So thank you for inviting me to this workshop and to have the chance to speak here. And also it's a pleasure to be here in Vienna for the conference in honor of Gordon Savin. My talk will be about building a theta correspondence in families. So maybe let me just first state in which setting I'm working. So I consider F to be a local non-Archimedean field of residual characteristic P and residual cardinality Q. So here, in general, when we are dealing with pairs of type 1, we exclude the case where the characteristic of the field is 2. But when you're working with type 2 dual pairs, the Weil representation in this context still makes sense. So you can talk about the Weil representation for type 2 dual pairs when the characteristic is 2. So when G is a connected reductive group over F, I will denote the following: G, which is the pro-order of the group, which will be some infinite multiplicity for P, and here you will get a natural number, an integer, that is prime to P. So for instance, when you're considering the pro-order of GLN of F, it is more or less, so this part is given by more or less the pro-order of your maximal open compact subgroup. So the definition of the pro-order is just the least common multiple of all these pro-orders of open compact subgroups. And so when R is a Z1 over P algebra, I will denote rep R of G to be the category of smooth representations with coefficients in R, and this to be the set of irreducible representations of two isomorphisms. So when R is the complex field or any characteristic zero field, I will call this situation to be the complex or classical situation. So the representation theory of p-adic groups has been extensively studied in this context. There is also a different coefficient ring that we can consider. Is a positive characteristic field where the characteristic is different from P. And so we usually call it the modular setting. The study of such representation has been initiated by Marie-France Zineras. She was interested in congruencies between automorphic forms. And also another reason to study them is some result in the fashion of Secher-Stevens, where they can prove results about the complex Jacquet-Langlands correspondence using some congruencies using various L's. So it's not only a problem that is related to representation theory, but has many applications. And so you can consider representations in families, that is over Z1 over P, or the Witt vector of FL bar, as long again as L is different from P. And you will call this situation working in families.
Or represented to any module?
Sorry?
Or do you mean R3 module with bijection, or you can? So do you mean the module is R3, or you can require some torsion in the module?
If I can, sorry, I cannot hear you.
I mean, in the last cases, what is the representation of R representation?
A smooth representation here. It's an RG module that is smooth in the sense that.
So you only require it to be a R module. You don't require it to be R3 module.
No, I'm not. Okay. No, it can be any RG module that is smooth with the usual condition of strong continuity. And so I will consider type 2 dual pairs, which are GLMD, GLMD, where D is a division algebra, let's say a division algebra over F. And the Weil representation in this context is the following. These are the locally constant, compactly supported functions on the set of matrices of size nm. And so this is a representation of your two groups. Of the product of the two. And you've got the following action. Which is given by the left and natural left and right action of matrix multiplication. So let me recall what is known in the classical and modular setting for the theta correspondence for type 2 dual pairs. So in this section, R will be an algebraically closed field of characteristic L. So I recall different from P, even if R is Z1 over P algebra. We've got the following theorem that is due to Roger Howe for complex coefficients or characteristic 0, and Mínguez for positive characteristic. So we suppose that L is not dividing the pro-order of these two pairs. And so this situation, you call this situation banal. Then the following is holding. So it's a kind of way to rephrase the usual bijection we've got. So if you take the irreducible representations of GLMD that are contributing, then this corresponds via the theta correspondence to some irreducible set for the other group of representations where pi prime are irreducible representation of the second group when this representation is contributing, so when the biggest isotypic quotient is non-zero. And this is characterized by and so this will be in this setting theta of pi prime, and this will be theta of pi. So it's a bijection that is usually denoted the same way, no matter which direction you are going to. And so this theorem is what I will call the theta correspondence in the banal setting. So what is known in the non-banal situation? Actually, little is known. So non-banal is L is dividing the pro-order of one of the two groups. one of the two groups in the dual pair. So you can produce counterexamples. So for instance, you take the pair GLN of F, GL1 of F, with R being FL bar, and satisfying the following congruence. Then the Weil representation is surjecting on this representation where this is just the composition of the determinant and the norm of F. And so a first remark that may be important in this case is that here, one and the norm, they've got the same supercuspidal support. So when n is 2 and q is -1 model, for instance, there is this representation, the induced of the Borel of the trivial character. So this I will denote and this way when the induction is not normalized. And this has circle, the trivial representation. It has cosoccle being the norm. And it has a cuspidal, non-supercuspidal, irreducible subquotient. So what do I call cuspidal in this context? Cuspidal representations are representations that are killed by all the Jacquet functors, whereas supercuspidals, and it corresponds to not appearing as a subrepresentation or a quotient of an induced representation. Whereas supercuspidal means not appearing as a subquotient of an induced representation. And so, of course, all supercuspidals are cuspidal, but there exists representations that are cuspidal, non-supercuspidal. Also, in this context, you are losing a lot of usual key properties that you may be used to, such as the projectivity mode center of cuspidals. That is true in the banal and complex setting, but that fails in the non-banal situation. So you may ask, why focusing on type 2 dual pairs? Because there are much more applications for type 1 dual pairs. So first of all, the Weil representation in this context is a simpler toy model. And this may give intuition for type 1 dual pairs. I'm saying that 2 is not implying, but may help understanding the type 1 case. So for instance, Roger Howe produced a proof for type 2 dual pairs that he refined as a proof of type 1 unramified dual pairs for p different from 2. That was refined for all type 1 dual pairs by Weil-Spurger for p different from 2. And also Mínguez, Alberto Mínguez, has produced a different proof for type 2 dual pairs that has been adapted by Gan and Takeda to type 1, what I call commutative dual pairs for all p. So commutative means that these pairs are built from non-quatern unique pairs. And for quatern unique pairs, using some identities, Gan and Soon completed this picture. So these are all for the classical setting, And this proof of Mínguez is also working in the modular setting as long as L is banal, the situation I described. And in my PhD thesis, I've been extending the proof of Takeda in the context of modular setting as long as L is banal. So I've got some assumptions, but anyway, the theta correspondence for type 1 dual pair commutative in the modular setting when L is banal should be something that is true. It's something that we expect to hold. Another reason for studying type 2 dual pair is that there is an explicit description of the classical or banal correspondence in terms of Lagrange parameters. So of course, there are a lot of work about Lagrange parameters for type 1 dual pairs, but in the case of type 2 dual pairs, this description is quite simple. And another reason why studying these type 2 dual pairs in families is that the representation theory of GLN of F, or maybe later on considering GLN of D, is better understood in the modular setting as well as in families. So when I mean it compared to type 1 pairs. So for instance, in GLN of F, there is the unicity of supercuspidal support in the modular setting for any L, so for any characteristic L fields, but this is not holding for groups that are in type 1 dual pairs. For instance, in SP8, you've got the non-unicity of supercuspidal support that was proved by Duda in the finite case. So for finite groups, that has been lifted by that, Jean-François Dat, to p-adic groups. So let me give now some motivations that are related to Lagrange correspondence. So now we denote GK to be GLK of F. And so the Lagrange correspondence is a bijection between the set of irreducible representation of GK to the Frobenius semi-simple Lagrange parameters. So here all of them is complex up to conjugacy. And this picture, you can see it as what I call the semi-simple Lagrange correspondence, which is obtained by looking at the set of supercuspidal supports. And here you can semi-simplify parameters. So again, up to conjugacy. And this map is again a bijection. And there is another way of seeing this semi-simple Lagrange correspondence. This set of supercuspidal support, they correspond to the C points of the Bernstein center. So that I denote ZC of GK. And here, these correspond to the C points of the ring of invariant of moduli spaces of Lagrange parameters. I will denote it x gk hat of C to mean the complex parameters, and you are interested in this ring. So this semi-simple local Lagrange correspondence, actually, you can see it as a ring isomorphism between this ring of invariant and the Bernstein center. In the modular setting, there is a semi-simple local Lagrange correspondence defined by Vinieras, which, so again, if you look at this set, it's corresponding to the semi-simple parameters over FL bar up to conjugacy. And this thing here are the FL bar points of the Bernstein center with coefficients in FL bar. So the Bernstein center is the endomorphism of the identity functor of your category. Maybe I should say it. And here you can see also some FL bar points of a ring of invariant, and this is again a ring isomorphism between this space of invariant functions on the space of parameters and the Bernstein center with coefficients in FL bar. So in families, there is a first step towards having these pictures in family. There is a local Lagrange in families defined by Emerton and Helm. Sorry?
What is the assumption on L in the...
Here. There is no assumption on L.
And they are reduced to...
No, they are not. They are not, but they are still corresponding to the FL bar points. So it's just that the map between them is defining this map, but you don't know that this ring is reduced, so it's not because you've got such a map that is realizing this map that you can deduce there is a unique one. So over the bit vectors, with some compatibilities with some compatibilities to the local Lagrange correspondence, semi-simple local Lagrange correspondence defined by Vinieras, and the modified, local Lagrange correspondence defined by Boy and Schneider. Maybe if I, so that I can finish on this, because then there is also the local Lagrange in families in the forthcoming paper of that Helm, Kurinchuk, and Moss that claims that there is an isomorphism between the invariant ring of parameters with coefficients in Z1 over P and the Bernstein center. So how can we translate this picture in the context of the theta correspondence? We can have some motivations. So we've got a theta correspondence that is a correspondence between some set of irreducible representations. And here we can take the supercuspidal support. And here it defines a semi-simple local Lagrange scope, a semi-simple theta correspondence. For some supercuspidal support that are contributing. And this is again a bijection. So if n is bigger than m, then the set of irreducible of Gn are all representations, which means that all representations are contributing. And this map, you can define it explicitly looking at the form of the Weil representation. I will define it in the context of non-normalized parabolic induction. It will be pi tensor 1. Here you've got the torus of size n minus m. And so you are associating to this supercuspidal support this one. And this is a morphism of varieties. It comes from a ring morphism between the Bernstein center of Gn and that of Gm. Ralis, in his work studying the unramified theta correspondence, has been studying unramified representations, and he's using for studying type 1 dual pairs, an argument coming from type 2 dual pairs, and he studied it for, so call this map theta C SS sharp. And he's been describing it between principal blocks. Okay, now, similarly, this holds over FL bar as long as L is Banham. So due to the work of Mínguez, there is a bijection here replacing C by FL bar with the assumption of L, and this factors through a map of supercuspidal supports. So it defines theta of FL bar, theta of FL bar semi-simple, and this ring morphism. So now I can state our main result. So what we want is, we want maps that will be defined in families and that will help recover by best change all these different maps that I've just written. And so our main result is the following. So I will denote here Zk to be the Bernstein center with coefficients in Z1 over P of Gk. And also I will assume that n is bigger than m. So there exists a map, theta mn, going from the Bernstein center of Zn to that of Zm, such that we can look at the natural map that goes into the intertwiners of the Weil representation. And you can describe the kernel of this map. So it has kernel generated, so it's an ideal, generated by the following elements for Z in Zn. So point 2. If you look at theta and n, this map is the contragradient involution of Zn. So I didn't mention it, but the theta correspondence when n equals m for type 2 dual pairs is just sending your representation pi on its contragradient. And this contragradient involution is a map that is defined on Z1 over P that is corresponding in some sense to the contragradient. So there are also inductive relations of this kind. Sorry, this way. So as long as k is between n and m. So for this map, theta and m is a finite map. That is, Zm is a finitely generated theta and m Zm module. And 5, theta and m agrees by phase change with the map I've been defining before, I've been mentioning before, ring morphism, where I've been only defining it when L is banal, but I recall that L is banal. And in the situation of A, these maps are surjective. And so in particular, this results in these maps being closed immersions.
Is a statement, so
Sorry?
What do you mean in the situation of A?
I mean, when L is banal, or considering these maps, when L is banal, these maps are surjective maps.
And it was not previously known?
Sorry?
This was not previously known?
Rice has been working in the context of principal blocks, and he's been proving the surjectivity in the case of principal blocks, and actually, we can prove it for pretty much any block using the same kind of idea as Rice. But as far as I know, The surjectivity of this map was not known. Maybe it is, I don't know. So how do you prove the first point? So the first point is proved the following way. So you've got the filtration that is given by the rank. And this filtration, it has subquotients being of the following form. Being some induced representations. Here I'm not normalizing the inductions. So the reason not to normalize them is just working on over Z1 over P, but you could normalize them adding a square root of Q. And so we've got the following key lemma. That is the fact that the endomorphism ring of these subquotients is isomorphic to the endomorphism ring of the regular representation. And this turns out to be exactly the isomorphic to the Bernstein center. And the second point is the fact that if you try to look at the intertwiners between these subquotients, so they are 0 if k is strictly less than k prime.
For these subquotients, is there some smaller Weil representation appearing or not? There's no.
I don't think so. There should be a CC infinite of GK, but is it? Or is it?
I guess I was asking whether you also have, because the parabolic PK has Levy GLK cross GL
so
n
this
minus
is parabolic GK times GN minus K.
So you don't see a Weil representation for GL n minus K or GL m minus K, no?
Because this is type 2, and so maybe you're thinking about the parabolic restriction of the Weil representation, where there is a smaller Weil representation that appears, but this is not the.
Oh, I got it. Yeah.
This, so how do you prove it? You use the geometric lemma, and plus the following fact: the fact that any GK morphism of a character into the regular representation is always 0. And so now you can take Y in the center. So Y, if you look at its image into the endomorphism of the Weil representation, it has the following form. You choose a basis that is adapted to your filtration. Because this element is in the Bernstein center, you will get a 0 here, because Y is preserving any sub-representations. And actually, this thing is also 0 because of the lemma, of the point B in the lemma. And so what you've got is that this thing is determined by all the images of your element of the Bernstein center on your subquotients that are just elements in ZK. And so you can define this map to Y you associate this W and MK, and it has the following nice property. They satisfy. So the kernel of phi n MK contains the kernel of phi n M, and this kernel, you can prove that it is given by a function between Zn and Zm And here, in this situation, this first piece is also a sub-representation. It's just the induced from PMN to GM of CC infinite of GM, and so on. And this thing is also here a sub-representation. So carrying on the proof, we can look at the second point. So this thing is really coming from the fact that this is the regular representation. And as this is the regular representation, if you look at the action of the Bernstein center here, you can transfer it on the other side. But looking at the action of the Bernstein center on the right is taking you some contragradient involution. So I will prove point 4 before point 3. Not the right one. So regarding point 4, you can have an alternative description of this map theta and m. So looking at the form of W and M that I've just been writing, you can write it another way. So that Kurinchuk and Moss have been proving that there is an Harish-Chandra morphism in this situation, which means that you can go from the Bernstein center of Gn to the Bernstein center of your Levy. So this is the Harish-Chandra morphism. And here, what are you doing? You are applying this contragradient involution. And here you are applying a character of the Bernstein center which is given by the trivial representation. So now, having this description, these inductive relations, they are coming from so this trivial, because the induced is not normalized, you can always include it in some bigger induced representation. And you can have induced representation in stages and use the this to prove that here, and so you apply Harish-Chandra morphisms in stages. So regarding 5, the point A is just coming from the fact that omega n m is compatible to changing coefficients, so to base change. And regarding the point B, so if you start with an inertial pair, phi m, so I'm working when R is a field, here. Sorry. Is a field with banal characteristics. So this pair, you can write it in the following form. You are requiring that K is maximal with this property. So you take your inertial pair, and you can always write it factorizing by your principal part, given by your principal block, so the multiplicity of unramified characters in this, and you can always put it this way. And so the map I'm considering is, in this case, the following. So So this thing is, because we are in the banal situation, you can write it in the following form. Of the principal block. And here you are applying the contra-gradient involution, and here you are considering a Rayleigh's map. And so this Rayleigh's map is killing n-m variable and is compatible with the ring of invariant description of the Bernstein center. And this thing is the Bernstein center associated to pi m. And this map is surjective. So to finish, maybe I will, because time is running short, I will just make some quick remarks about this theorem. So if you look at I and 5b, yes, A and 5b, and also 5a, the base change, you can prove something like, so when I prove it, I'm not assuming the theta correspondence. I'm just assuming some relations that I can prove in characteristic 0, so I'm not assuming the full power of any other results. And what you can prove, for instance, is if you take the biggest pi isotypic quotient of the Weil representation, it will define big theta of pi. In this situation, in the banal situation, you know that it has a unique irreducible quotient, or it is 0, but let's say it's non-zero. And because it has a unique irreducible quotient and being finite length, all its irreducible subquotients will have the same supercuspidal support. But the point is, this is implying not only the fact that all its subquotients have the same supercuspidal support, but also the fact that the center of the other group is acting as a character. So which is a much stronger result. And in particular, you can prove that if you consider eta a character of your Bernstein center, you look at the biggest eta isotypic quotient of your Weil representation, the other Bernstein center will act as a character. So which implies in particular the conservation of supercuspidal support. Another remark is you can look at the various idempotents here and look at their images. So for instance, if you know because of the compatibility with Bayes change, if you know that in characteristic 0, the level is preserved, then you know that it's preserved for Z1 over P, just because of this morphism and the fact that these rings are flat over Z1 over P, so they embed into the Bernstein center with complex coefficients. And another way of thinking is you can look at this map in terms of affine varieties. And so you can ask, where are the irreducible components and the connected components sent? And this is a question that is really interesting because when you work in the modular setting, you've got your connected components that are containing several irreducible components. Your irreducible components, after inverting the non-banal primes, are going to become connected components. And so you can look at your congruencies between your blocks that are mod L and the connected components that are colliding. And just to finish, maybe a last remark is that, so this map, we try to prove that it's surjective, but as far as we know, we are not yet able to prove it. So in terms of a map of supercuspidal supports, you can always define a map on supercuspidal supports in the over FL bar when L is non-banal, because you can compute using the filtration there, you can compute a map between supercuspidal supports. But as Gaëtan Chenvier mentioned, it's not because you've got a map there that is agreeing on supercuspidal supports, that this is the right map you've got to consider. Especially because these rings may not be reduced. And another, to finish, another situation when I wrote the local Lagrange correspondence is this map is coming from, is defined over Z1 over P and is defined for the parameters for the semi-simple correspondence. And so you can also describe on the Galois side the theta correspondence in terms of parameters. And we hope that there is a description, so it's really vague what I'm going to say. There is a description in parameters that will be, that you can achieve over Z1 over P. And that this description will pass because it's an obvious, so we've got a good candidate. It's an obvious morphism between the spaces of Lagrange parameters. You can take the quotient stacks. And so it gives you a morphism between quotient stacks, and then maybe we can use it to deduce things on the representation theoretic side. Thank you for your attention.